This is the wrong slide. Is it last one? I mean, I can do it.
Okay. Yeah, welcome back everyone from the lunch break. We had some last-minute change. Luckily, Isaac was nice enough to fill the gap, and he will tell us about constant depth, so constant t-depth circuits. Please take it away.
Okay. Yeah, if you're wanted to hear about Heisenberg model, sorry to disappoint you, but you're going to have to come back tomorrow. I was supposed to talk about this in the a fault tolerance day, so I'll think of it as like a prelude to tomorrow's session. Okay. So let me start off with some broad remarks about fault tolerant quantum computation. So I guess for this audience, I don't have to belabor this whole point, but there's a current physical error rate that we can currently hit, and there's some a target a logical error rate that people are aiming for in the future, and the gap between the two seems rather large. But the good news is that, in theory, we know how to bridge this gap. This is what all the theory of fault-tolerant quantum computation is about. And there's a large amount of effort in this direction. And in this business, almost all reasonable fault-tolerant quantum computation scheme is based on some form of a stabilizer code. This is there's some select small setup schemes which does not rely on that, but I would say 99.9% of every reasonable scheme is based on stabilizer code, and that immediately limits the kinds of logical operations that you can do. So by the Easton-Knuth theorem, you cannot hope to really achieve a continuous set of fault-tolerant logical operations. You're really limited to a discrete set of gates. And in the stabilizer formalism, you have this nice hierarchy of gates that you can quantify in various ways, that you can organize in various ways, that are luckily related to, it seems to be related to how difficult they are to actually implement in practice. So at the highest level, we have this thing called a Pauli operator. So the logical Paulis are simply the tensor product of physical Paulis, and therefore it's the depth 1 circuit. Applying them is very easy. This is not an issue. But of course, that's not enough to do a universal quantum computation. We need a really universal set of fault-tolerant gates. And to complete that, we need these two extra set of gates. The one is the Clifford, and the other is something that lies outside of the second level of the Clifford hierarchy. Generally speaking, it's not exactly the case that these are the Cliffords are always easy to implement, but given a reasonable quantum error correcting code, usually there is some way of figuring out some Clifford gates. And to the extent that you can probably figure out a complete set of Clifford gates that generates the full Clifford group. So this is not something that I'm too worried about. The something that worries me, or I guess many people in error correction, are these things in the third level Clifford hierarchy. The most famous example is the T gate, or there's also CCZ or CCS gates. And for a long time, the usual route for preparing them has been based on this preparation of so-called magic state. And if you wind back for 10 years ago, not sure if many of you would be working on this, but there were some discussions just the cost of preparing these magic states is so high, so expensive. How are we going to actually build these things? This was a very common discussion point. And the reason for that was because almost all reasonable ways of generating these logical magic state was based on the so-called magic state distillation protocol. This is due to seminal work by Bravi and Gitaev. And simply put, you put in some noisy magic states that are encoded in some logical subspace, and you run through some Clifford operations. And at the output, you get some more distilled magic state. The upshot of this approach was that the scheme is very flexible. So in any situations where you have a complete set of Clifford, logical Cliffords, you can simply implement this. And the threshold for this working is also very high, something like 19%. But if you actually plug in the numbers, you quickly realize that the cost of running this magic state distillation scheme in its original form is at least 1 or 2 orders of magnitude more expensive than the most elementary Clifford, logical Clifford gates, such as the logical C0. And it has been staying that, it had been staying that for a very long time until what in my mind were very important developments by Gideon Fowler and also Litinsky, who, it's a bit engineering, but the point was that if you have a distillation scheme that consumes magic states in a multiple level, at the lower level you can sort of use like a smaller codes because the quality of the magic state that you're going to get is not going to be that good, so it doesn't make sense to use like a very high distance codes. And that led to a like pretty significant improvement, but even after that, there was still some noticeable gap. The good news is that this story has finally changed over the past few years. And I'll tell you a little bit about that story, although that's not going to be the main point of this talk, to give you some motivation. So I would say around year like 2019, 2020, people had some very Redder-specific and highly optimized diagrams for preparing logical magic states like CCZ, and you would see some monstrosity that looks like this. But in the meantime, there are some somewhat orthogonal line of works that try to prepare magic states in a different way. And the idea was to use some small codes that are efficient at generating some magic, but with in a low distance code, and somehow like grow that into a larger distance code that you're going to eventually care about. So this idea actually goes back all the way back to 2014, actually 2016, I would say, by Goto. But it was relatively underexplored until you might have heard about this recent development called like magic state cultivation or code switching protocols that actually made this idea work in practice. So. So starting from this rather expensive ones, these like recent approaches led to actual like experiments preparing a logical magic states. And for those of you who are not like too deep into this like experiment side of things, in all these experiments, the key point is that the fidelity of the encoded magic state is strictly better than the fidelity of the underlying physical error models. Like for example, in the experiment that I was involved with, the 2-qubit physical error rate was around 1.1 times like 10 to minus 3, and the fidelity of magic state was around like half of that. And there are also these nice experiments, another one by Quintinium and also by Google, which like undoubtedly demonstrated that this line of idea works. And you can ask me more if you're really curious about this, but if you really put like a tally of the total space-time cost of this protocol in achieving this error rate, and if you compare like the logical C0 and the logical magic state, they're really not that different actually. So this like old paradigm in which magic states were very expensive is changing very rapidly, and it's experimentally this is definitely happening. And in the future, there are many places, certainly almost all the ion trap-based quantum computing companies, they're aiming for a physical error rate down to 10 to minus 4. And if that happens right off the bat, you're going to get roughly at least 3 orders of magnitude like improvement starting from these guys. Yeah, so even better than these things. So I think it's very conceivable that these non-Clifford gates will become quite cheap in the future. In my mind, this is like almost an inevitability. So these days, I've been thinking more about like in a world in which these non-Clifford gates are much cheaper than we think, that we used to think. How should we really think about quantum compilation? And that's what I want to talk about today. One of the early examples in this early works in this direction, which I think is interesting, is due to Austin Fowler, which was expanded upon by Daniel Litinsky, 2018 further, which is that if you really have like a huge quantum computer and you can apply these like T gates in a really fast way, ultimately what matters is that constrains the total computation time is the T depths of the circuit. Roughly speaking, say you have a circuit consisting of Clifford and T gates, and imagine organizing them into different layers that either consist purely of Cliffords or purely of T's. And you basically try to minimize the number of independent like T layers as much as possible. And the minimum attained number is called as the T depths. And I guess what these folks show was that the ultimate, like if you really push for the speed, the ultimate time applying a quantum computation is basically the t-depths of the circuit times the measurement time at the physical level. This is assuming that decoding is like super fast and all that. So that's what I want to think about. So if in a world like suppose we want to like really optimize for t-depths, what can we really do? This has some like very obvious implications for like fault-tolerant quantum computation compilation, but there's also been some interesting observations that somehow they come up very naturally in various complexity theory setups. I will not discuss that in today's talk. What I want to tell you about today are some very like a basic subroutines, like sort of like the first thing that you would think about how to implement on a quantum computer, and argue that they can be actually realized in like a very low t-depths. Certainly like much lower than I thought was possible. One example is rotation. Of course, given a single qubit, like applying a single qubit rotation is almost trivial experimentally. But of course, the problem at hand is that you have a universal set of gates, and you want to synthesize this arbitrary rotation angle theta using these like a discrete gate set. If you're kind of like deep in this like more like the applied side of like a quantum algorithm, you often see this. Unfortunately, I don't think there's a name for this, but it's something that I call as programmable rotation. Imagine you have a n-bit approximation of some continuous angle theta stored in some quantum register, and depending on the value of that angle, you want to apply a rotation which is exactly that angle. That's another thing that you may consider, and maybe it's obvious to you, maybe it's not, but a related thing is the addition. Like you're given two integers and you want to add them. If you just add them in over like a z, then this is not reversible, so you want to do like modular addition. And the claim is that all of this can be done in constant t-depths. That's really the main part of this talk. And actually, I'm slightly cheating, so you might notice that there are these star marks here. So the first two actually requires a catalyst state. If you know what that is, then good. If you don't know, I'm going to define them, so no worries about that. Any questions so far? Yeah?
Do any of your claims say something about the D count over here?
Not in this slide, but it will appear in, yeah. All right. OK. So let me first start with the rotation. So the problem is, simple. You're given a gate set, which is Clifford plus t, and you want to approximate this unitary, the diagonal unitary. It's one of the first things that you learn in quantum computing, generating a continuous gate set from a discrete gate set. And famously, there's a Solovay-Gitaeva theorem, which, basically solves this problem for like any universal gate set, if you have inverse. But for like rather specific gate set like this, you can often do a lot better. And there's another famous result by Ross and Selinger, who basically solved this problem optimally, essentially, modular an ability to factor some integers, but in practice it can be done fairly fast. And then there are some further improvements to this problem, which basically improve this constant to some smaller constant, like 1.1, something like that. And all of this is known to be optimal on t-count. But if you think about it, this is just like acting on like a 1 qubit or like a constant number of qubits. So the whole depth is just going to be like a log and like 1 over epsilon. Yeah, question?
How do these results relate to the thread of Sarnak and Orrin-Korchinski and all the
Yeah, so I think I only know Sarnak's result. And Sarnak's result generalizes the Ross-Selinger, but it doesn't strictly generalize every aspect of Ross-Selinger, but it generalizes for some aspect of Ross-Selinger to some more general gate set.
If I'm not mistaken,
Yeah.
like 2 weeks ago, the alpha was made into 1 and the O1 was removed by Orrin-Korchinski.
Oh,
But it's not up yet.
it's okay. We can discuss more, but so that work I may not know, but at least these works I know, and O1 is really there in this case, yeah. It's around like 8 or something. Yeah. Good. Anyway, so we want to do that. And there's actually like a pretty famous way of like realizing this rotation using a catalyst state. So for those of you who don't know what catalyst state is, what is that? So the goal is really to apply some unitary U like this to an unknown state psi. But you think that maybe, so the idea is that maybe you prepare a special state, let's call this a catalyst state, and you apply a joint unitary on both of these states together. And afterwards, you get the desired operation U on this unknown state, and this catalyst state remains unchanged. So the reason we call this a catalyst state is because if you compare the computation before and after, it remains unchanged, but it somehow like helps you with implementing this specific unitary that you care about. And I guess a really neat thing is that in many situations, using a catalyst state can actually help, like quantitatively, like in terms of like using fewer gates or like reducing the depths and so on and so forth. So it's instructive to like understand like how this actually works for this simple problem. And the idea is like almost like textbook like 101, like a quantum computation. So consider this state, which is obviously related to quantum Fourier transform. And imagine doing an addition by some fixed integer L. And you can see that, well, the point is that this is an eigenstate of this addition operation. So if you apply this unitary addition by L, you're going to get its eigenphase up here. So the trick is to simply just apply the phase kickback trick, namely you have a single qubit that's going to act as a control, and you apply the controlled addition, where the addition is acting on this QFT register. So if the single qubit state is in the 0 state, you don't apply the addition, so you don't accumulate any phase. If the single qubit state is in the 1 state, then you do apply addition, and therefore you accumulate this phase. So you get this desired single qubit rotation. Yeah. So in fact, in a world in which you just really try to optimize the T-gate count, the best thing to do is to apply the addition in some sequential way, like this way that you learn in elementary school. But if you want to really optimize the depth for it, there is a way of like doing this using log n depths. So I guess it's not too surprising that you can do addition in log n depths. So doing that, the T depths of this n-bit rotation can be actually brought down to like big O of log n. So it's very natural to think about whether you can do like better than log n. And you can quickly convince yourself that this is not possible. So for example, if you consider like these two different additions, like flipping a single bit, like just flips like every single other bit. And therefore, well, you can kind of think that there should be like some kind of Lycan argument that there should be at least like a log n lower bound. In fact, you can do a little better and show that there's a log n like Toffoli depth lower bound. And there's just no way around this. Technically speaking, in the quantum computing, on top of these Toffoli or T-gate, you also have Clifford gates. It's not clear if we still have a lower bound in that world. It's something that I asked around, and I haven't really received any like satisfactory answer. If anybody knows, please let me know. But that remains as an open problem. But intuitively, it seems like it may not help because Clifford, they're like rather limited. Certainly, it doesn't help you generate like extra Cliffords. Extra Toffolis. So if I were to guess, I would guess that maybe this still holds true, but we don't know. But in any case, from the perspective of this like catalytic rotation, it seems pretty obvious that we kind of like hit a dead end. We can't like really pursue anymore unless we solve this somewhat difficult problem.
So can you mean the first open question with Clifford?
So the question is, let's say you have like Clifford plus Toffoli gate set, and do you have like a log n Toffoli depth lower bound for addition or not? Yeah. as opposed to just like classical reversible circuit plus Toffoli. Yeah. Yeah. And somewhat surprisingly, there is a way actually, and the idea is based on the approach is to basically move away from like standard binary representation, which kind of feels like cheating, but there are cases in which this is sensible. So note that in the standard binary encoding, formally speaking, we really have elements over some cyclic group whose order is 2 to the n. And we can consider some cyclic group, which is actually the multiplicative subgroup of this binary extension field. So basically, this is a set of polynomials with binary coefficients mod by some fixed polynomial, which is irreducible. Basically, it's something that can't be factored further. And this both the addition group and the multiplicative subgroup forms a cyclic group. And in fact, the multiplicative subgroup is isomorphic to a subgroup, cyclic group of order of 2 to the n minus 1. Almost 2 to the n, but not quite. So the idea is something that sounds kind of dumb, which is somehow you encode your integers into this. So instead of doing addition, you do multiplication. Sounds like a bad idea. So you might wonder, how could this possibly help? It could help because these binary extension fields, they're actually quite rather nice. So imagine like explicitly writing down all the coefficients of these polynomials, like f0, f1, fn minus 1. So these are just all zeros and ones. And imagine you want to map, somehow you want to map this guy into g of f, by, g times f. By g times f, I mean you multiply those two polynomials and you write down all the coefficients, zeros and ones. Okay. The claim is that this is actually a Clifford. So do you see why this is true? Yeah. The reason is that this, given a fixed polynomial g, multiplying by g is a linear operation. So you have a linear operation on the set of these like binary vectors, and therefore it must be possible to realize this by a bunch of like C0 circuits. And of course, like C0 is just like all Clifford, so therefore there should be some Clifford unitary U that realizes this operation. And moreover, this U has a period of at most 2 to the n minus 1. Well, I guess it's sort of obvious if you know the order of the cyclic subgroup is, but what is the reason? Like imagine you pick some generator. So remember this cyclic group. So you pick a generator of the cyclic group. Let's call it as h of x. And you write down g of x as this generator raised to some power, write down f of x as this generator raised to some power, where alpha and betas are some integers. And in this encoding, you see that multiplying by u has the effect of like changing alpha to alpha plus beta. So we can have this pretty bizarre encoding in which to encode alpha, what do? You take the discrete log of this element of this gf 2 to the n, and and then write down that integer in your. Of course, you're not going to really do that. What you're going to actually write down in your register are these coefficients of the polynomial. But ultimately, this is how the encoding works. So if you were to use that encoding, you can see that everything that I said about this like catalytic rotation follows just almost exactly in the same way. The only difference is that the number 2 to the n changes to 2 to the n minus 1 because the size of the field has reduced by 1, which is really not a big deal. But you have this encoded form of the addition. So insofar as you prepare this state that kind of looks like a QFT state in some weird encoding, this phase kickback trick still applies with this angle. So by choosing the amount that you're going to add, you can get the desired rotation angle. Of course, we're not quite done because Cliffords are cheap. Of course, Cliffords are cheap, but when you control Clifford, it is not obvious whether you can make that into a constant t-depth circuit. If you use a textbook method, like imagine decomposing your entire Clifford into the set of like 1 and 2 qubit Clifford gates and controlling them like individually. In the worst case, you're going to have like big O of like n square such gates. So in the worst case, you're going to have actually big O of n squared Toffoli circuit, and the depths will be like linear in n. And you don't want that. But fortunately, it turns out that any C0 circuit can be actually controlled in a constant Toffoli depth. The reason for this is, like insofar as you believe some math result, it's like sort of obvious. But I guess the point is that for any, there's just like a very general linear algebra fact that if you have some n by n matrix over like arbitrary field, this could really be anything, then there is some similarity transformation such that you have this like block diagonal form where you have this a very sparse matrix. And the point is that these individual sparse matrix, they can be implemented in like a t-depths of actually 1. It's some easy fact that you can actually show. So once you know this, you sort of get like a couple of corollaries like pretty immediately. For one thing, suppose you have like an n qubit like general Clifford. It's like a very well-known fact that this can be decomposed into a sequence of layers, each consisting of either like purely Hadamard's, purely S gates, or purely like C0 layers. So you can imagine controlling each of these individual layers like 1 by 1. The Hadamard and the phase operations, these are just like tensor product of single qubit unitaries. So parallelizing that control is like trivial insofar as you have this fan-out operation. The only non-trivial one is this controlling like C0 layer, but that's the case that was handled by this like previous theorem. So immediately we get that any Clifford can be controlled in constant t-depth circuit using constant t-depths. In fact, more generally speaking, if you have any Clifford plus t circuit of depth d, then even after you control it, the t-depth remains the same, basically. So if once you use that trick, you get a t-depth, which is, there's some asterisks here, but it's essentially 1, basically. So you can do like arbitrary rotation using a catalyst of size of n. You will need like more qubits for some ancillary like qubits for like fan-out operation, but the catalyst size is really like literally exactly n. And for like n-bit precision rotation. And yeah, so that's what you get. A somewhat funny story is that before this like optimal result was found, I had this like a result which was like pretty suboptimal. And the next day, Craig, who's very fast at these things, like came out on Twitter and immediately realized that t-depth can be reduced from 3 to 2 and the size can be reduced to n. And the very next day, he wrote another tweet saying that actually it can be amortized all the way down to 1 plus epsilon, where epsilon is an arbitrarily small constant that you can tune with n. But in the end, we got something slightly better. OK, so admittedly, the one sort of bad thing about this of these approaches is that we're sort of like completely ignoring the Clifford cost. So in all the schemes, especially the optimized ones, I think they have a Clifford cost of like big O of n squared, and I don't see a way of reducing them. But there's some special case in which you can actually reduce the Clifford and Toffoli cost all the way down to like a depth all the way to the constant if you have like measurement feedback. And this is when you have like a fixed rotation angle. So imagine, and I guess the paradigmatic example is maybe these like mini experiments that people are imagining like running on like quantum computers in the near future, like maybe you have some 1D like brickwork circuit, and you have all these angles which are like exactly the same at each other within a single layer. Or maybe there are a few of them, and they're just being repeated using like the same pattern. In that case, what you can do is that you can prepare like a specialized catalyst state for, say, this angle, and you just use that until all the way up here. And in the meantime, you can prepare a catalyst state for the next layer and just recycle them through. So it's not like a super like a generally useful thing, but I just want to say that in some cases you can do even better than just simply like a constant T-depth circuit. You can actually almost get almost like a constant Clifford depth as well. And the way that works is again like similar, but instead of using something like very generic about GF2 to the n, you can use some like very specialized constructions. For example, in this GF2 to the n, we had this like a polynomial that we're like modding out by. Sometimes we can choose that to be what called as like a primitive polynomial. If f of x is a primitive polynomial, then it just so happens that every power of x ends up being that like covers all the non-zero elements of the field. So what you can do is that you can go through the entire multiplicative subgroup by starting with x, and you multiply it to x squared, x cubed, all the way to like x2 to the n minus 1. And the results will be all distinct. And I guess the nice thing about the construction is that the matrix corresponding to multiplying by x is like extremely simple. It looks exactly like this, where these f's are the coefficients of this primitive polynomial. And you can sort of stare at one of these guys, and you can see that, oh, this just looks like a cyclic shift. And indeed, this is a cyclic shift. So, and the second one is just a C0 operation from a single qubit to some set of target qubits. So of course, the cyclic shift can be just realized using a constant depth circuit, like a depth-2 swap circuit. And this like a C0 operation from a single qubit to multiple target may seem like a problem, but the thing is, there are some hobbies out there who just constructed these like primitive polynomials up to like pretty large values of n, all the way to like n in 660. And apparently for every such n, there's a primitive polynomial with non-zero coefficient, number of non-zero coefficients at most 4. So for the purpose of applying a rotation with precision which is lower than 660 bits, this part will just use like 4 C0 gates. That said, for larger precision, we don't know. Yeah, maybe you might get unlucky, and this may not happen. So using that, basically, the version, the very first version that came out, which was admittedly suboptimal in terms of T depths, could actually have a like much better like Clifford depths. Basically, all the Clifford in this whole procedure comes from the fan-out operation. So actually, in many quantum error correction architectures, this will be almost like an order 1 time like operation, because like fan-out, for example, in the surface code will be just like yeah, you can do it very easily. Good.
Sorry, what do you mean by type?
Sorry?
The type column, what does that mean?
Oh, good. So these are for fixed means that you make a catalyst state targeting a specific rotation angle. Variable means that you have a universal catalyst state that is usable for any rotation angle. So like there's a way, like if you think about it, if you can generate like n, like the fixed rotation catalyst state, that is enough to generate like arbitrary rotation. And that's why you see this gap between n and like n squared. Yeah. Good. Okay. So yeah, that's like a one conclusion. So apparently any rotation, you can do it in constant T depths. And if the rotation angle is fixed, with measurement feedback, you can actually do it in constant Clifford depths as well. But there's if you go to some applied quantum computing papers, you actually not see these like single qubit rotations much. You're going to see something that is more sophisticated, which is you have some encoding of your rotation angle in a quantum register, and you would apply a rotation whose rotation angle is exactly that. So for this, you can sort of imagine applying a similar trick, this like addition trick, but there's a slight difficulty, namely. Of course, if you can somehow do this like in-place addition of like adding alpha, like alpha into alpha plus beta, then everything that I said, like let's say 10, 20 minutes ago, will just like carry through. And you will be able to actually apply this operation in constant T depths. And in fact, there's a lot of motivation for doing this because this just appears in so many different places, like here. But the issue is that this is no longer a linear operation. So for a fixed f, of course, like multiplying a fixed f to an unknown g is a linear operation in G. But if both f and g can change, this is not really a linear transformation anymore. So how do we deal with that? There's one simplification, which may not seem that crucial, but it does matter. What it does is that you can change this requirement of doing in-place addition in this format to an out-of-place addition. Generally speaking, out-of-place addition is easier than in-place, so this kind of reduction is not always possible. But in this case, this is possible. And the trick is actually rather simple. So instead of storing the polynomial as is, you store the polynomial and its inverse simultaneously at the same time. Of course, because this is an element of the multiplicative subgroup, the inverse of the polynomial is also a polynomial. So this will also have some, stored, like its coefficients will be binary, and you just need to store those like a binary information. So how would this work? So imagine you have two registers storing f and g. These are polynomials. What you can do is that you can do this out-of-place multiplication, storing the product of f and g into this register, and storing the product of f and g inverses on the other register. But of course, after you do that, you somehow want to erase this thing, g and g inverse. And how do you do that? If you sort of stare at this, you can see that there is a way of removing this g and g inverse by multiplying two things in a crossed way. For example, you can multiply this f inverse and fg together, after which you're going to get a g, and you can add that g into this register. And because everything is like a binary coefficient, they all just cancel each other out. The same with the inverse part. And you could just swap these two registers, let's say, the middle part and the right part, to basically get let's see, f inverse, fg, and fg inverse. Sorry, this is supposed to be the encoding of fg, not g. So with this trick, you can upgrade this like out-of-place multiplication into the in-place multiplication. But of course, the bigger question is, how do you actually do this out-of-place multiplication? It doesn't change the fact that this is still a nonlinear operation. And you would think that this is hard, but actually, there is a way of like rewriting this in the following way. So imagine you have two polynomials, you multiply them together, you expand everything into this product of these coefficients and x raised to the I plus j. This is obviously correct, but the thing is, this operation is clearly bilinear in f and g. So you can write down the most general form of bilinear form in terms of coefficients of f and g. And what's the most general possible thing? You take the dot product of this vector consisting of the coefficients of the polynomial f with some vector, let's say CL, And you do the same thing with some vector g, with the coefficients, vector consisting of the coefficients of g. You take the product, and then you add up some polynomials. Okay? And believe me, this is the most general form possible, and this is a valid expression. The real question is, once you rewrite your formula in this way, what is the minimum possible R such that this can actually describe the product of f of f and g? Trivially, you can choose R to be n square. If you look at this like a naive expression, there are like naively like n square summations that you have to do. And you might think that you can't do anything better than that. But there's a pretty remarkable fact, which was discovered by the Chinovsky writers in 1988, who showed that actually this R can be chosen to be at most linear in n. This is a non-trivial fact. And I won't go through in the details, but we can talk offline if you're curious. But once you realize that linear in n is possible, then it sort of becomes obvious like what you get from the quantum computing perspective. So let's just dissect this equation like one by one. So here we have a dot product of two vectors. So this CL is just a coefficient, like a fixed vector, consists of like ones and zeros. F is this unknown vector, and we're trying to take the dot product of the two. This is basically doing an XOR of like a bunch of bits. So this can be realized by just some C0 circuit. Same with the dot product of G and DL. DL is just a fixed binary vector, and G is the unknown. So you have, for each L, you get 2 bits, one from here and the other from here. And you're like adding this particular polynomial if and only if the product of those two is 1, which is only possible if both of them are 1. It's just a Toffoli gate. So in fact, these individual, you can see that you can imagine like running a big C0 circuit so that you get this bit value for like every single R, like in parallel, like using, actually not even using like any Toffoli at all. And then you do this like a parallel Toffoli. So in fact, all these like these bit values BL, they can be computed in like Toffoli depths of 1. And so you write down all these bit values for BL, and based on that, you do you're basically adding this like a polynomial. And they have like binary coefficients, so this is just XORing a bunch of things. Again, it's just a C0 circuit. So this whole thing, even though it looks complicated, it's just like a C0 circuit, like a single layer of Toffoli, and just a C0 circuit. Of course, you have to uncompute, but that's also just another Toffoli. So this whole thing actually has just a Toffoli depth of 2, and using linear space, actually. So it should be noted that actually this argument works like no matter how large the R is. So even if like R is like quadratic in n, this would have been still like a constant Toffoli depth, but the space would have blown up to be like a square, like n squared. So what they, so my students are here, so they can correct me if I'm wrong, but the original paper actually showed the existence of such a circuit, but it took a while for people to actually come up with a constructive algorithm for finding this CL and DL. So you would like to actually use this for somebody gives you, somebody gives you a number of bits n, and you would like to be able to compute the value of like CL and DL in polynomial time. And that was published like relatively recently, just a few years ago. At least that is a claim. But unfortunately, it seems very difficult to implement this algorithm in practice. I guess a fair thing to say is that the AI tried and it failed. It required some understanding of some standard algebraic geometry book from the 1960s. And that's the part that it stopped working. But there is these folks also have a constructed polytime algorithm that has a slightly worse scaling in terms of R, almost linear, but n times log star of n, basically log, 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 until it just becomes, basically linear. And for that, the AI did succeed in actually coding it up. And you get something that's not exactly linear, but for n up to 40, the rough scaling seems to be like around like a 6.5n. So with all those ingredients together, what we see is that indeed, out-of-place multiplication can be upgraded to in-place multiplication in this case, and in-place multiplication can be used to do programmable rotation. And everything, because I've shown you that we're controlling a Clifford plus T circuit with constant T depths, the control version also has a constant T depth circuit. So you conclude that this operation that you often see in, let's say, quantum chemistry, application of quantum computing, this actually admits a constant T depth circuit. So I guess, sorry if this talk was like more of a too many examples type of things, but I think the moral of the story that I want to deliver here is that these are like such basic operations that I thought that obviously constant T depth circuit would not exist for them. But somehow surprisingly, there seems to be these like understudied areas in mathematics somehow tells us that that constant T depth is actually sufficient. So this space of constant T depth circuits actually seems surprisingly powerful and rich, and I think it's an interesting problem to explore this area further. So in fact, I don't want to spend too much time on this, but yeah. But there's an old result by Hoyer and Spalek who said that if you can do, their result implies that if you can do rotation in constant T depths, then all these operations like topoli on like n bit for arbitrary n, or addition, multiplication, quantum partial Shor's algorithm, that can be all realized in constant T depths. So like in particular, if you have a catalyst state, it implies already that all these things can be done in constant T depths. And in my mind, a very interesting question is, can you do this in constant T depths used without any catalyst? This remains open, and it's not clear at all if that is possible or not. Good. So to conclude, we seem to have a surprisingly rich space of constant T depth circuits. There are all sorts of interesting things that we can do. And there are these open problems that it seems rather challenging, but I would really like to know the answer to. For example, are these like rotations or like standard addition like possible in constant T depths without catalysts? If it is impossible, what is the no-go argument? None of this is very obvious to me. With that, thank you for listening.
This silicon for out-of-place multiplication. I don't know the best intuition for this, but do you know if this is died?
Sorry, I couldn't hear the
Oh,
question.
sorry. I'm just asking if this silicon for OB multiplication is died.
Oh, I see. It is linear. Let's see. The main cost is really here, like it. Well, I guess it's out of place, so you need another register. That's really the main ancilla cost. Yeah.
Any more questions? I've got one. So you said like this primitive polynomials, essentially like the hobbyist community kind of finding them. So first of all, like what kind of goes into finding them, and then have you tried kind of throwing AI at it to kind
Sorry, what was the second question?
Have you kind of tried to kind of just kind of throw in Claude at this problem?
Oh, no, I have not actually. Oh, you mean the existence of
Yeah.
Oh, I see. I have not. So this was before they became much better. So yeah,
I see.
but yeah, I can. Yeah, we can. Yeah, maybe. Yeah.
Any more questions? Okay, then maybe like one follow-up question. So how does it kind of affect like resource estimate costs for like doing Shor, for example?
I think it's not yet clear. So the issue is that the Clifford costs, once they become n squared, they seem to become pretty big in practice. So I talked to some these people who are like more in tune with like quantum chemistry, and I was told that the value of n that I should focus on is around like 15-ish, and in that regime, the Clifford cost is actually pretty big compared to the T-gate cost. And I guess an interesting question is, this is a situation where you know you're going to apply the same Clifford like many times, and I wonder if it's possible to actually amortize them in some way.
Okay. So it's kind of TBD.
It's a TBD, yeah.
Okay.
Yeah.
Okay. Thank you. All right. If there are no more questions, let's thank Isaac again. And we have another coffee break, and then we meet again in half an hour. Half past.